Hi, everyone. It's 12:55, so we can get started. Um, there is one announcement on homework 2, problem number 8. There was a small typo. It's now been fixed. So whether or not you've done that problem or not yet, you'll want to make sure that you look at the current homework file, either finding it on Canvas or Gradescope, just to um, take a look at problem 8 because there's been an adjustment. All right. With that in mind, let's begin. So here is the first problem. We're going to be doing a lot of proofs today. Here's the first one. Prove the product of an odd integer and an even integer is always even. Take a couple minutes to do that, and then we'll do it together. All right, so we can get started on this problem. So it says that the product of an odd integer and an even integer is always even. So if we want to talk about integers, then we need some integers. So we need to introduce a little bit of notation. So let's let our integers be x and y. So x is going to be some integer in z, and y is going to be some integer in z. And we're going to say that one of them is odd and one of them is even. That's the setup here. So the product of an odd integer and an even integer. So okay, so let's let x be even. So that means that x equals 2m, where m is an integer. And also, we know that y is going to be an odd integer. So y is equal to 2j plus 1, where j is in the integers. Okay. Are there any questions about the setup? Let me that's not a C. That was going to be a parenthesis, but it looks weird. All right, so that's the setup. And now we just want to make sure, or we want to show that the product is even. So we have an odd integer and an even integer. We want to show the product is even. So does anyone else want to do it? Would anyone else like to draw on the board and show that the product of X and Y is even? All right.
I
That's
could
okay.
try, but I by no means know the answer.
Well, if you all right, I'll do it if maybe on another one, if someone has some ideas that they have in mind and they think they might be right, then maybe they can do it. So, but
I would
if go ahead,
start
Alec,
by-
what's up? Sorry.
I would start by multiplying 2m and 2j plus 1, and then mess with it for a while, and eventually it should work.
Yeah, so that's the right strategy. So we want to show that x times y is even, and we have these two quantities here, and even numbers are 2 times an integer. So that's our integer. So we somehow need to take this and make it look like 2 times an integer. So
We factor out the 2 and then say that like mj plus m is a integer by closure, and then say that mj plus 1 is c, which is in z, and it's 4 times 2c, and so that's even.
exactly, yeah. Yeah. So just to illustrate what he was saying, he's saying he's going to factor out the 2, and then he's going to multiply m by 2j plus 1. But here he recognizes that integers are closed under addition. So 2j plus 1 is an integer, and m is an integer. And integers are closed under multiplication. So that means that m times 2j plus 1 is an integer. So, and we're multiplying it by 2, so we know that x times y is even because we've just shown that it's 2 times an integer. So, so let's just say, let me just write out that right here, we need to be able to say that this thing is an integer, and we can, due to closure of the integers of z, closure of z under addition and multiplication. Addition and multiplication. Okay, so I'll just put it times there. Are there any questions about this problem? All right. If there are any, you can always let us know later. So let's move on to this next problem. So this one, use induction to prove that for every integer n greater than or equal to 1, n cubed minus n is divisible by 3. So take a couple minutes and then we'll do it together. I think someone has their microphone on. If you could turn it off, that would be great. All right, so let's get started on this one. Since we're doing induction, we need a predicate. So does anybody want to tell me what the predicate's going to be here? So the predicate is what we're going to show as true for every integer n. So what is the predicate? You can type it in the chat or shout it out, whatever you want.
Is it just n cubed minus n is divisible by 3, or?
Exactly, yes. Yep. And then we're just going to write that concisely, which is that 3 divides n cubed minus n, which is exactly what you just said. It's just I'm using symbols that allow me to write it without as much writing. So, okay. So now we need to show that this is true for P of 1, P of 2, P of 3, P of 4, P of 5, and so on. So we're going to use a standard technique, which is induction. And so the first thing we'll do is prove it for a base case. And the base case is going to be the first case, which in this case is n equals to 1. So that's the first integer. So that's our base case in this one, because we want it to be true for every n greater than or equal to 1. So P of 1 is that is the statement that 3 divides 1 cubed minus 1. So let's see, I'm just going to write this out, P of 1. So we're going to be doing P of 1. This is proving that P of 1 is true. And to do that, we write out what n cubed minus n is when n is equal to 1. That's 1 cubed minus 1. That's equal to 0. And 0 is equal to 3 times 0. And 0 is an integer. And so therefore we conclude that 1 cubed minus 1 is divisible by 3. Or in other words, 3 divides 1 cubed minus 1. And so we say that P of 1 is true. Are there any questions about P of 1? All right, and then in the inductive argument, we're now going to assume for some arbitrary integer n that P of n is true, and we're going to prove that P of n plus 1 is true. So let me just write out what we're going to try to do here. We want to prove the following statement. We're going to let n be some natural number, and we want to show, so WTS is want to show that P of n implies P of n plus 1. So we want to show that this implication is true. So we're going to assume that P of n is true and use it to show that P of n plus 1 is true. And then once we do that, we'll that will complete our inductive argument, and we can talk about why we're done once we do this. So, but this is the standard induction framework. We're going to find and prove the base case, and then we're going to prove this inductive step, which is that if we assume P of n is true, then we must be able we must be able to show that P of n plus 1 is true. So, all right. So let's try to do this. So what is the goal? We want it. Let's say we're assume. So let's assume P of n. Okay, so n is some natural number, and we've just assumed P of n. We want to show P of n plus 1. So what is P of n plus 1? Does anyone want to say or in the chat or shout out what we want to show right now?
Can I ask a question?
Yeah.
Haven't in the inductive examples that I've seen, I thought we normally proved Pn minus 1, but here we're doing plus 1. How do we make that decision?
So it could be made arbitrarily because both methods are going to give us P of n for every natural number. So you can just choose it based on what you think might be easiest for you. I didn't even think about it when I did it like this. I mean, I didn't choose to prove P of n implies P of n plus 1 because I thought it would be easier. I just did it because that's valid, but you could have easily decided, I'm just going to assume that P of n minus 1 is true and prove P of n.
Okay.
You could have totally done it that way. The only difference is that you're doing that for every n greater than or equal to 2. Here, when we try to do that, P of n implies P of n plus 1, we're doing it for n greater than or equal to 1. So, but both are going to be just fine.
Okay, thanks.
Yeah. So, all right, I guess I'll write out what P of n, so P of n plus 1, what we want to show then that P of n plus 1 is true, and that means that we want to show that n plus 1 cubed minus n plus 1, that this is divisible by 3. So we need to show for some integer that, some integer, that'll be an integer, q will be an integer, that this is true. So as I think, you've seen in class, we're going to try to simplify this expression a little bit. And how we simplify it depends on what our inductive hypothesis is. This is our inductive hypothesis, that P of n is true. And so in proving that this statement is true here, we're going to try to use P of n. So I'll just write up here what we're going to be using, which is that we know n cubed minus n is equal to 3z, where z is an integer. Z is an integer. This is in the integers. So we know this. We want to show this. And so we're going to try to simplify the left-hand side here so that it looks, so that this term pops out, because we're assuming this, so we want to use it. So let's try to use it. So if we take this expression, let's just factor out an n plus 1. Let's just try to simplify it. So you could use the binomial theorem to write out n plus 1 cubed with all of its terms, or we can take out an n plus 1. So there are different ways to try to simplify this, but ultimately we need to simplify the cubic term. So I'm just going to take out an n plus 1. So because there's an n plus 1 here and there's an n plus 1 here, so we can just take it out. And that's going to leave us with n plus 1 squared minus 1. Okay, so we're not quite done yet because we need something that has an n cubed and a minus n, so we're not there yet. So let's keep simplifying. So this is n plus 1 times n squared plus 2n, and then there's a plus 1, and then we subtract 1, so the 1 cancels. Okay, so still we don't have an n cubed, we don't have a minus n, so let's keep going. So we have, let's just distribute here, we have n cubed plus 2n squared plus n squared plus 2n. All right, so, okay, this is starting to look better. We have an n cubed. That's good. So we still don't have a minus n, which that's not great, but So we'll have to keep simplifying. So let's do some more stuff here. So this is n cubed plus 3n squared minus 2n. Okay. So we still want to use our inductive hypothesis, which is up here, and we haven't used it yet. So the issue is that we have a minus 2n. We don't have a minus n. So sorry, that's a plus 2n. Yeah, sorry. We have a plus 2n and not a minus n. So we're still not there yet. But we can now be clever because we know we need a minus n and we don't have it. So we can try to make an equivalent expression for 2n that involves minus n. So in particular, I'll just write this up here. We can rewrite 2n as 3n minus n. Okay. So this it's, you know, this is true obviously, but it's actually very helpful to us because now we have a minus n, and we can use that. So in particular, we have, this is a cube. We have n cubed. Now we have minus n. Okay, that's good. And then we have, well, now we have a 3n, because remember we have this term here. So we have plus 3n squared, 3n squared plus 3n. Okay. So we're almost done. Now we're going to use the inductive hypothesis to write this as 3z plus 3n squared plus 3n. And then we're going to factor out the 3. And then we would argue that that z plus n squared plus n is an integer because integers are closed under multiplication and addition. And so therefore, this expression is divisible by 3. So we conclude that Pn plus 1 is true. Are there any questions about that?
How do you know that 2n is 3n minus n?
So n is just n is a number. So n is a variable. You can think of it like apples. Like n is a quantity of apples. So 2 apples is equal to 3 apples minus 1 apple. So n is some number. N is just a number, and so, you know, yeah, is that n is a yeah, n is a variable. So this algebra works. Yeah, does that help?
Kinda, yeah.
Okay. Okay, sorry. What you can do here to see this, just write 3n minus n as n times 3 minus 1. So here we just factored out an n. Is that a little more convincing?
Yeah, I see that a lot better now.
Okay. All right. Yeah, so what we just proved is that if Pn is true, then Pn plus 1 is true, and that was for an arbitrary integer n. So we are done with this problem, and we only have to understand why. So effectively, we've completed the inductive proof, but we have to understand why this worked. So we showed that P of 1 was true, and remember our goal was to show that for every natural number n, P of n is true. So we showed that P of 1 is true, and we also showed that for every integer n, P of n implies P of n plus 1. So if P of 1 is true, then by this statement, which we just proved, P of 2 is true. So we have P of 2. And since this statement is true, for every integer n, it's true for n equal to 2, which means that P of 3 is also true. And this goes on as long as we need it to go on. So if someone comes to us with an arbitrary integer k, and we want to show that P of k is true, then we would be able to argue that it is true by going through this step of saying, okay, P of 1 is true, therefore P of 2 is true, therefore P of 3 is true, and so on. So we have just proved for every integer n in the natural numbers that P of n is true. So we're done. Are there any questions or confusions about any of that?
I guess one question I have is, will we be using the same strategy for kind of these induction problems where you prove for any like base equation like n is greater than wildest? Will we use the same strategy of proving P of 1 to be true, and then we go on to prove the implication of P of n implies P of n plus 1 to be true? Is that kind of the strategy we'll be using for these type of induction problems in the future?
Yeah, the only modification, the modifications might come from what the base case is going to be. So we have to kind of answer each problem as it comes to us, and there will be slight differences that come into play. But in general, you're always going to have to prove a base case and then prove an inductive step, which takes the form of showing that if Pn is true, then Pn plus 1 is true. So what the base case might be could be different. So maybe someone will ask us to prove that if n is greater than or equal to 11, that n cubed minus n is divisible by 3, in which case the base case is now P of 11 and not P of 1. So some things might vary, but this general strategy of finding a base case and then proving the inductive hypothesis, proving that P of n implies P of n plus 1, that will be similar throughout.
Okay, sweet. Thank you.
So, all right, let's get on to the next one. Okay, so because of time, let's just take 1 minute to think about it, and then we'll hammer this one out. All right, so I know that wasn't too long to think about it, but there are some other problems that it would be nice if you guys get to see today. So, and including this problem. So, so let's do this one. It says that if n is not divisible by 3, then n squared plus 2 is divisible by 3. So for this one, we're going to use, I think what this is called in the book is the division theorem. So n is not divisible by 3. If we draw like a clock, then it has this 1 and 2. So basically all of the numbers fall somewhere on this clock. So for example, 0 falls here, 1 falls here, and 2 falls here, but then 3 falls back at 0, and then 4 falls at 1, and 5 falls at 2, 6 falls back at 0. And what's going on here is that all of the numbers that are multiples of 3 are falling at 0 on this clock. And all the numbers that are not multiples of 3 are falling at 1 on the clock or 2 on the clock. And so that's some intuition for the division theorem, which we're now going to state more formally, which is that if n is not divisible by 3, then one of two things must be true. One of these things must be true. Either case 1 is that n is equal to 3j plus 1, where j is an integer, so this represents n falling at 1 on the clock. Its remainder is 1 if we were to divide it by 3. And the other option, if that's not true, then n falls at 2 on the clock. So n is 3j plus 2, such that, I'm not going to use j just because that can be a little confusing. We'll just use I, where I is in Z. So one of these two things must be true. Either the remainder is 1 or the remainder is 2. So, and in particular, we can either express n as 3j plus 1, where j is an integer, or we can express n as 3i plus 2, where I is an integer. So that's what the division theorem says. If a number is not divisible by 3, that's what it says. So we'll now handle the first case and show that n squared plus 2 is divisible by 3. So under case 1, well, if we want to show that n squared plus 2 is divisible by 3, then we're going to write out, we're going to try to simplify n squared plus 2 and show that it can be written as 3 times some integer. So let's start with n squared plus 2. And whenever we're doing a proof, we want to try to use what we know. And what we know in case 1 is that n is 3j plus 1. So that is not that's a 2, sorry. This is a 2. So we plug in what we know, 3j plus 1, and then we are adding 2 to it. This is a square, and then we add 2. Okay, so let's do some distributing. So this is going to be 9 times j squared plus 6j plus 1 plus 2. All we did was we distributed the 3j plus 1 squared. And so this term here is 3. So all 3 numbers here are multiples of 3. This is 9 is, all 3 numbers are multiples of 3, so that's a big hint. We can factor out a 3. We can factor out a 3. So we factor out a 3, and we're left with 3j squared plus 2j plus 1. All right. And now we would use our usual arguments to show that this is an integer. We say, well, integers are closed under multiplication, so j squared is an integer, and so is 3j squared, and so is 2j. And then we say, we use the fact that integers are closed under addition to say that 3j squared plus 2j plus 1 is an integer, and thus we conclude that n squared plus 2 is divisible by 3. So that's the first case. And then the second case is very similar. So the strategy is very similar. So does anyone have any questions about this problem? All right, so for practice, I recommend that you work out the second case, but again, it's going to be a very, very similar strategy. There we go. Okay, so let's do, we have 13 minutes left. All right, let's do this one. So state whether the following statements are contrapositives of one another, and describe the traits a counterexample to each statement must have. So the first one, if you like computers, you would love computer science. So Okay, so I think, okay, Alec is stating that these are not contrapositives, and that's right. The second statement, so remember, contrapositive of a statement is, so we have P implies Q, and the contrapositive would be not P, and not Q implies not P. So here the statement P is you like computers, that would be P, and the Q statement would be you would love computer science. So the contrapositive would be, if you do not love computer science, then you do not like computers. And then Joey says those are converses, and the this is called the inverse. So remember, the converse is just where we flip the terms. The converse would be Q implies P. The inverse is not P implies not Q. So so that's exactly what's happening here. If you do not like computers, then you do not like computer science. So that's the inverse. And then let's look at one for a counterexample. It says, if you like computers, you would love computer science. So so does anyone want to provide what would, oh, here, Alex has something. So the question is, well, we need, if we wanted to show that the statement was not true, then what would we have to provide? That's what we're asked here. That's what it means to describe the traits of a counterexample to each statement. So again, if we wanted to show that statement one was not true, then what information would we need to provide? So Alec has some suggestions. So he says we would need to provide someone who likes computer science but does not love computer science. That's exactly right. So that would mean that the implication is no longer true. And what he's doing is, we want to show that P implies Q is not true. So we have to provide an example where P is true, but Q is not true. And then that's number one. And number two is done similarly. P is called the hypothesis, and Q is called the conclusion. So, all right. Are there any questions, any other questions about this problem? I know we did that kind of quickly. I think the possible mistake here is to provide a counterexample where the hypothesis is false. Well, we want to show, so Alec brings up something to discuss here. We're trying to show that an implication is not true. So in order to show an implication is not true, we need to show that there's an example where the hypothesis is true, but the consequence is false. Because remember, in the truth table for an implication, implies Q, we have true, okay, true, false, false, true, and false, false. So an implication is only false when the hypothesis is true and the conclusion is false. That is the only time it's false. Because remember, we always assume that an implication is true when the hypothesis is false. So that means that the way to show that an implication is false is to show that we can provide an example where these conditions are matched. In particular, that the hypothesis is true and the consequence is false. So are there any other questions about this one? All right, if you do, sorry that I didn't give you much time to ask questions on that, but let's just take a look at this last one because of the time. So we have 8 minutes, which is plenty of time to start looking at this one. So it says, prove that 7 is the only prime number that precedes a perfect cube. Okay, so let's just start doing this one. And yeah, let's just start doing it. So we want to prove that 7 is the only prime number that precedes a perfect cube. So the perfect cubes can be represented as integers taken to the third power minus 1. Sorry, the numbers that precede perfect cubes are the numbers that take this form for some integer x. So what we want to show is that if this thing is prime, then it must be 7. So again, to repeat the framework for this problem, we want to show that 7 is the only prime number that precedes a perfect cube. All of the numbers that precede perfect cubes have this form for some integer x. So what we want to show is that if this thing, if some x cubed minus 1, some perfect cube minus 1 is indeed prime, then it must be 7. That would show that 7 is the only number that precedes a perfect cube that is prime. So that's the setup here. So we take a number, a perfect cube. So let's let x be in the integers. Then, and we're going to now assume that that x cubed minus 1 is prime. Okay, so I've just denoted t as x cubed minus 1. So t is prime. This is our, we've just found we're now claiming that we have found a number that precedes a perfect cube that is prime. We have just found one. We must show that it is 7. That is the way to prove this statement. So we must show that t is 7. So t is prime. We're given that t is prime. We must show that t is 7. So how are we going to do that? We're going to factor x cubed minus 1, and we're going to use the formula for differences of cubes. So you may remember from calculus or algebra or one of those that to factor a difference of cubes, this is going to be a minus b times a squared plus ab plus y squared. Okay, so here we have a difference in cubes because 1 is a cube. So that means that we can write this as x minus 1 times x squared plus x plus 1. All right, so we've just found a factorization for t, and the claim is that t is prime. So this means that one of two things must be true. So here's case 1, that x minus 1 is equal to 1, and x squared plus x plus 1. Remember, t is prime, so its only factors are 1 and itself. That means that x minus 1 must, if x minus 1 is 1, then x squared plus x plus 1 must be t. Also, we're skipping, well, we're not skipping a step, but remember that this is a factorization because both of these are integers, because integers are closed under addition and multiplication. So this is an integer and this is an integer, and that's why this is a factorization of t. So we know t is prime. So the first case is that the first term is 1 and the second term is t. And the only other possibility is that the first term is t and the second term is 1. All right. Okay, so let's deal with this second case first. So, and let's look at this. We know that x squared plus x plus 1 equals 1. So we can rewrite that as x squared plus x equals 0. And in particular, this means that x times x plus 1 is equal to 0. And that implies that x is equal to 0 or x is equal to 1. Okay, but that means, but this implies that t is either equal to -1 or t is equal to -2. All right, but the problem now is that t is prime, and by definition, all prime numbers are positive. That is part of the definition of a prime number. Prime numbers are defined they're only positive. So they are the numbers which are larger than 1, whose only factors are 1 and themselves. And so they're defined to be positive, and therefore this is a contradiction. This cannot happen. So that means that case 2 is impossible. So we could only be in case 1. And in case 1, from this equation, well, this means x is equal to 2. All right, that means x equals 2. So now we go back up to t, we plug in 2, and we get 7. So we plug in 2 here, and we get 7. So we've just shown that t must be equal to 7. So, so again, the framework was we took an arbitrary perfect cube minus 1. We claimed it was prime, and we showed that it must be 7. And therefore, we have concluded that the only perfect cube minus 1 that is prime is 7. So it's 3:45, but I'll stick around if you guys have questions about this problem. And otherwise, yeah, otherwise that's the end of today's problem solving session. But I'm happy I'll stay for a couple minutes in case there are questions.
Yeah, I have a question about the first case, or right by the number 1, you have, it says x minus, is that a v, or what is that?
Oh, that's a 1.
That's a
Yeah.
1. Okay, gotcha.
Yeah.
Where did that come from again?
That's coming right from here. The 2 factors. This is the first factor and this is the second factor.
Okay, gotcha.
Yeah.
Okay, cool. Thank you.
Yeah. Mhm.
Like, do we supposed to remember that a to the third minus b to the third is that 2 factors? Like, because I don't remember this formula.
I don't think you need to remember. I'm guessing you don't. James, do they need to remember that first? No.
I don't know, on like a quiz or something. I mean, I don't think it's too far out there. So it might be some of these tricks I might just put in your note sheet. Because a lot of like these problems with numbers and stuff deal with knowing how to factor numbers, and a couple little tricks like that you should have learned at some point. So I don't think it would hurt just to put a few of those on your note card.
I just write it down so I can use it later.
Thank you.
Oh.
All right. All right, I'm going to log off for the day, but James has office hours at 2 p.m. That's in 10 minutes. So if you have additional questions, he will be there. So, all right.
Thank you.
Yep. Have a good day.